Let's now take a closer look at quantifying some of those currents from the previous video. So we're still talking about an NPN device, which is in the forward active mode, so FAM. And so let's start by considering our base emitter junction. And so of course recall, since we had our forward active mode, we're saying that this base emitter junction is forward biased. And so because it's forward biased, we can sort of, as a first order at least, use our ideal diode equation to describe the current across it. So we can say that our emitter current, I sub E, is equal to some IEO, which is sort of like our reverse saturation current for that junction, times E, and now instead of our diode voltage, we have this base emitter voltage, V sub BE, divided by our thermal voltage, VT. We're going to ignore the ideality factor, the N, we'll just assume it's 1, and then minus 1. Well, it turns out if our base emitter voltage is high enough, we can just ignore this -1 term. So let's say that this is approximately just this IEO times E to the VBE over VT, our thermal voltage. So again, VT is the thermal voltage, which is equal to KT over Q, roughly 26 millivolts at room temperature. So this IEO here, this sort of reverse saturation current for that base emitter junction, is based on our electrical parameters, size of the junction, so geometry. Typically it's going to be in the range of 10 to the minus 12 to 10 to the minus 16 amps. So similar to what we saw with reverse saturation currents in our diodes. So now let's talk about our collector current. So we've talked about our emitter current. So now let's turn our attention to our collector current. And so we know that our collector current, I sub C, is going to be ultimately proportional to the number of electrons. So I've got a symbol there for, so it kind of looks like an alpha, but it should be more like that. So it's directly proportional to the number of electrons which are reaching the collector. And of course, if we're talking about a current, we're talking about per unit time, so charge over time. So number of electrons reaching that per unit time. And now we know that if we're depending on these electrons that are coming from our base emitter junction, then that is going to be proportional to our base emitter voltage. So proportional to the BE junction voltage. And so again, all that is, if you think back to the previous video, we had a figure showing our gradient for our electron concentration. And on that left side, we were always injecting more electrons. How many electrons we inject ultimately is going to be proportional to how many electrons make it to the other end on the right side to our collector. And so what we see with this sentence is that basically the voltage across two terminals, so voltage across our base emitter junction, is controlling or directly proportional to our collector current. So voltage across two terminals controls current through the third. And so, as you remember from a couple videos back, that's our basic transistor action. So we can write our sort of rough equation for our collector current I sub C. We can say this is equal to some reverse saturation current I sub S times E to the VBE divided by VT. Again, VT is our thermal voltage and VBE is our base emitter voltage. So notice, to a first approximation, there's no dependence on that base collector voltage. So let's say first order, no dependence on our VBC, or our base collector voltage, so long as it's reverse bias, I should say. So long as our BC junction remains reverse bias. And so the reason we want it to remain reverse bias is so that we want to stay in that forward active region. So if it changes, then we're going to be going into our saturation region. Okay, so we have no dependence on that BC junction. for our collector current. So what that means is that this is basically acting like a constant current source. So it acts like a constant current source, and we can say that because it has a constant current, again, to first order, regardless of the voltage across that junction, so long as it's reverse bias. So again, emphasis on first order. This is just an approximation, but it is acting somewhat like a constant current source. So we've considered our emitter current, we've considered our collector current, so now let's briefly consider our base current. So our base current, remember we said had two components. We had a component due to holes being emitted into our emitter from the base, and we had a second component, IB2, which was due to recombination of holes and electrons. So this IB1 is our hole current that was being injected into our emitter. So holes injected into emitter. And so I had mentioned in the previous video, we can make this small by appropriately doping the two regions. So small because our dopant concentration in our emitter is much greater than our dopant concentration in sub A in our base. And so again, that's something we're not going to get into too much, but you can just kind of take my word for that. And then our IB2, we talked about, this is our recombination current, and we had said in the previous video we can keep this small just by keeping that base width small. So recombination current, and we can say this is small with small base width. And as we talked about in the first video, our base widths are typically on the order of tens to hundreds of nanometers, so quite small for the base width. And so we can ultimately just approximate this as some IBO e to the negative VBE. So again, it's dependent on that base emitter voltage divided by our thermal voltage VT. So what you'll notice is that I didn't box any of these current equations, and that's because these aren't the primary equations that we're going to be using when we're talking about currents in our transistor. So in the next video, we're going to look at how we relate these three currents, and it turns out that these are the equations that we're more often going to be using when we're doing DC and AC analysis on our BJTs.